So we'll be discussing Green's functions for inductors. Okay. So we'll be doing here in today's class Green's function in one dimension. Then we'll go to the higher dimensions. Okay. Okay. Why we require Green's functions? Okay. Suppose if you are having, let's say, inhomogeneous differential equation. Let's say if you are having simple differential equation, dy by dx is equal to 0. So this homogeneous equation, there is no source term for this whole equation. So you can solve it. You can solve it exactly. So what is the solution? What is the solution? Y is equal to c. Y is constant. Okay. Okay. Now if you are having this kind of equation, dy by d of x is equal to f of x. Okay. So you can solve it exactly. It's a very simple differential equation, but this equation is having a source here. We call this term as a source term. Clear? Okay. So there is no derivative on it. We will call this as actually a source term. Okay. We can solve. Okay. So this is simplest of the differential equations. We can solve this exactly. What is the solution for this very differential equation? So you can write constant of integration, let's call that as y naught plus integral dx prime and fx prime. Okay? From some up to some x. Clear? This x can be integer. So, clear? So this is how we solve this kind of differential equation. Now in general, if you are having some differential equations which are inhomogeneous, they are usually very difficult to solve. Clear? Okay, for that matter, we require, okay, instead of solving a differential equation for a given source, what the source is given, so this can be completely arbitrary. What we do, we solve an equivalent equation for a point source. Okay, what I mean by that, let's write. Suppose if you are having this differential equation, well, let's say I don't know the solution for this differential equation, and this f of x is completely arbitrary. Okay, so it's a it can be very complicated function or it can be simple function. Clear? And I don't know what kind of function it is. What I will do, I will solve instead a differential equation. Let's say for some function g, okay, we satisfy this kind of equation. Okay, it is also an inhomogeneous equation, but an inhomogeneous equation for a point source. What I do, instead of solving this equation completely, I will solve an equation, an equivalent equation for a point source. Okay, so this kind of equation is easier to solve. Okay, so g is the solution of this very differential equation. From this g, I should be able to construct this y, because y is the solution to this very differential equation. Okay, and I am solving this differential equation. Okay, from this g, I should be able to construct the solution. Clear? Samajh? Okay, if I do it in this way, then I call this function to be a Green's function. This g we call as a Green's function. Clear? Okay, so Green's function is a solution to a inhomogeneous differential equation solved for a point source. Clear? Okay, so let's take formally these definitions. Okay. So what I will do, let me call some operator Lx. Okay, so this is a differential operator. Okay, so let's act this as y, and you are having an f of x. So Lx is a differential operator. Okay, so this Lx can be, okay, x means it is differentiating at point x. Okay, Lx like this thing. It can be simply d by dx. Okay. It can be what? d2 by dx2. Okay, it can be, let's say, d2 dx2 plus d by dx plus some constant and so on. Okay? So this Lx can be anything. Yeah? Clear? So I am considering only in one dimension. That means I am considering differential equation with respect to only one variable. Clear? Got it? Okay. So I am having this. Now you got what Lx means. It is simply a differential operator. So if Lx is d by dx, So it will be dy by dx equal to f of x. If it is like this thing d2 by dx2, so it will be a differentiation on this y equal to f of x. Clear? Okay. So what I will do, okay, let's define a function, okay, some g of xx prime such that, okay, I am having like this thing, this Lx acting on the g xx prime is equal to this delta of x minus x prime. Okay, so I am solving what? Okay, a corresponding differential equation for a point source. Okay, this g, there is a physical interpretation. Okay, in general you can think this Green's function as a response function to a point source. You got my point? So there are various interpretations for this Green's function. Physically, broadly speaking, this is a response function to some external source, to some external perturbation. Okay, now let's say if you hit somebody by a pin, needle, okay, what will happen to him? So he will feel, okay, something, okay, he will respond to that shock, is it? So how you measure that shock? I mean the response. In simple terms, that is the Green's function, okay? Green's function will help you to measure that kind of response. Clear? Let's say if you are having some system, let's say some system of electrons and a gas of electrons, okay, let's say some electron gas, okay, you perturb it, okay, now you measure something, okay, because of this perturbation there you measure a response due to that perturbation, okay, so that response will be given by this Green's function, okay, clear? So this is the physical interpretation of this Green's function. Okay, how to construct the solution? Okay, so look here, before figuring out the solution, you are having this inhomogeneous differential equation. So there are actually two solutions for this differential equation. Okay, rather two parts of a solution. What are those two parts? One is the homogeneous part. You solve a homogeneous differential equation and then figure out a particular integral, is it? Particular integral corresponds to the inhomogeneous part, okay? So the solution here consists of two parts, homogeneous plus particular integral. Okay, homogeneous you know. You simply, okay, so it will be like this thing, Lx y0 equal to 0. Yes. So y0 is a homogeneous solution to a differential equation. You solve it, you know how to solve a homogeneous differential equation. Now then you need to figure out a particular integral, is it? Okay, when you try to figure out the particular integral, you need to take into account this source term. Clear? Okay, so you can take this Green's function, help us to evaluate this particular integral. Clear? So the inhomogeneous part of the solution. So therefore, okay, let me write now the solution. The solution corresponding to this very differential equation is, okay, y is equal to y naught. This is the homogeneous part, okay. So let me write, okay, so this is the homogeneous part, okay, plus an inhomogeneous, corresponding to the inhomogeneous part, what we call the particular integral, you write like this, dx prime, g of xx prime, and f of x prime. Okay, now let's check whether this is really a solution or not, okay. So let's operate, okay, so therefore I can write this Lx acting on y is equal to Lx acting on y naught plus integral dx prime. Okay, Lx, since Lx means the differentiation with respect to x, so it will act on which objective? This object, is it? So it should be like this in Lx acting on g of x prime, okay, f of x prime. Okay. So what is Lx acting on y naught? It is a homogeneous part, it is equal to 0, is it? True? Plus integral gx prime, what this object is? By the definition of the Green's function, it is a delta function. Okay, x minus x prime and f of Now you integrate over, what you will get? Simply f of x. So Therefore, we are having this Lx y is equal to, we have got differential equation back, is it? So it means this is the solution corresponding to this differential equation. Got it? So we'll be mostly interested in figuring out this Green's function. Okay, if you specify f, then we can figure out the solution as well. Clear? But we'll be only doing calculating the Green's functions in various situations. Okay? Once you know the Green's function, the solution is easy to calculate. Clear? Okay. Okay, so let's take a general consideration. Let's do it in some general way, all these things. Okay. So we start with this Lx acting on y is equal to f of x. Clear? So now let's write it in terms of the Dirac notation. For y, okay, I'll write this operator simply as operator L. Okay, let's write it in the cat-car notation. So for this y, I'll write a cat y. For this f, I'll write cat f. In a very simple way, huh? Clear? Okay. So y, okay, cat y means it is y, and cat f means it is this f. Okay. So now, if this L is invertible, okay, so it is simply now the operator equation. So what we need to figure out? This y, is it? Okay. So corresponding, since this is an operator, I have put an operator L. Clear? So this is now an equation. Now what we try to figure out? This y. Y is the solution of this very equation. What I need to do? I need to invert this operator. Is it? Okay. Let me write. Let L inverse be the inverse of L. Clear? So therefore you can write like this thing. L inverse L acting on y is equal to L inverse L. Clear? So what you got? Y is equal to L inverse L. Got it? So let's write this L inverse as G, where G is equal to L. That means G into L is equal to identity. Clear? Okay. So now let's write, okay. So let's multiply by Abass state x on this y in this fashion. So it will be x G. Clear? So this I can write y of x is equal to. Now let me insert an identity, completeness identity. Okay, so that, okay. So I can write this dy y, that's equal to identity. Okay? Clear? So is this a complete, is this an identity? What? Huh? Is it true? So how you write the position basis, identity? The completeness condition. How do you do it? Okay, so let's insert it. So I can write this this very product simply as y of x. So it's equal to x G. Let me introduce it here. Y prime, some y prime, and then we have. So you can write now this gy prime as x G y prime. Clear? So this I can write as gy prime. So this object I can write, since this is a matrix element, okay, x and y prime, the matrix element of this G, okay, like this thing, this I can write as f of y. Okay? So now you can see, so what is our y of x? So y prime you can, because it's a dummy variable, or I can write this y is equal to dx prime g of xx prime f of x. Okay, so we call this G as the Green's function. Clear? So we have constructed this solution, is it? But we have from here we have constructed it in terms of G, but I don't know what is an equation that G satisfies. Is it? So from this way, okay, if I start in this way, I don't know what is a corresponding differential equation or what is a corresponding equation that this G satisfies. We need to figure it out. Clear? Samajh? Okay. So it comes from here. So this very objective. Okay, because G is related to what? L inverse. Okay. So now let's do it. So you are having G. Okay, and let me write it this way. L G is equal to identity. Clear? So or I can write it as X L G Y. That's equal to. Okay, let me write X prime. X prime. Okay. So what this object is? This is an overlap between X and X. So it is this delta plus minus X prime. Clear? Okay, so now let me insert the same completeness condition here. Okay, let's insert that. So it is X, okay, L. So let me write some X double prime. Okay, X double prime, X double prime. Okay, then you are having G and X. G, X prime. So that's true. Delta X minus X prime. Clear? So it implies therefore G. Okay, please settle down somewhere. So why you are late, by the way? So I can write that as simply matrix elements like this thing. And then you are having X double prime G X prime. So it is G X double prime and X prime. So what that is equal to? So it is simply that you are rewriting this very identity. So this identity is in the operated form and you are writing it in the matrix form. Clear? So now you see this G satisfies this very equation. Clear? Okay, but if I know, let's say this, since this L comes from where? It's a differential operator. It is this very L, is it? Samajh? And this operator is a local operator. In a sense, because it acts only on one coordinate here, X coordinate. Okay, now let me give you an example. Suppose if you are having d by dx, so it will act only at the point X, clear? So you can call this as a local operator. Okay? So now if you are having this kind of operator, d by dx, let me write like this way, partial by partial x plus partial by partial x prime. Now this is a kind of operator, let's say, so which acts on where? It acts on both the points. So in that sense, you can call this as what? Non-local operator. This L is a non-local operator. Individually they are not non-local, but this collectively it is a non-local operator. Clear? Or you can have like this way, or partial by partial x, partial by partial x prime. Clear? So this kind of operator acts on 2 points, is it? So in that very case, it's a non-local. Okay? Now let's say this L is a local operator. What I mean by that, if L is a local operator, so it means this L x double prime, it's simply actually delta of x prime x double prime. So it forces x prime to be same as what? X double prime and Lx prime, let's say. Clear? So now look here. So this x prime, so this will be non-zero only for what? X prime is equal to x double prime. Clear? So much shown. So in that case, it is so it will act only at 1 point, not at 2 points. Now if you see, this is actually the matrix equation. So in other words, this is an operator which acts on both points. Okay, x prime and x double prime. But I am saying it's a local operator in that sense. It has to only define it with respect to a given point. So now let's write it. Okay, so therefore I am having this dx double prime. So I am having delta of x prime, x double prime Lx double prime, then you are having Gx double prime x prime, that's equal to delta x minus x prime. Now integrate over x double prime will be replaced by x prime, so it will be simply Lx prime. Clear? I think we have, no, it's not x prime, xx. So it's x and this, so it's not x prime, it's x, xx. So it will be simply Lx acting on this g of x double prime will be replaced by x prime will be as such is equal to delta x minus x prime. So that means this g has to satisfy a inhomogeneous differential equation, but for a point source. Okay, clear? We started with from this differential equation, and we saw the solution corresponding to this differential equation can be written in terms of this g. But then we figured out the g itself satisfies the same kind of equation, but for a point source. Got it? Okay. So now let's take examples. Let's try to figure out Green's function in certain cases. Okay, let's take the simplest of the case. Okay, I will just specify the operator because I need a Green's function with respect to a given operator. Then when you try to figure out the solution of a given differential equation, there are two ways to figure out. One is if the boundary conditions are not given. So then you can say the solution is indefinite solution. But if the boundary conditions are given, that's a definite solution, is it? But we will be doing the indefinite case because I have not specified any boundary condition yet. Okay, so I will then go to the definite case. Now let's say I am having this very operator d by dx. Okay, so it means I am having this kind of equation dy by d of x is equal to f of x. Now let's try to figure out what is the Green's function corresponding to this very equation. Clear? Or in other words, what is the Green's function corresponding to this operator? Got it? Okay, so what I need to solve for a Green's function, I need to solve this very equation. Clear? So in order to figure out this g Green's function, we have to solve what? G by d of x, okay, g of x prime is equal to delta x prime. Is that true? So it means I need to solve this kind of equation. Okay, differential operator is given d by dx, it will act on g, and this is the delta function. Now tell me, okay, so what is a function? So it is a differentiation of a given function that yields me a delta function, is it? Okay, now, let me ask you people, what is that function called? When I differentiate it, it gives me a delta function. Which function I can differentiate, it yields me a delta function? A step function, yes. Great. So look here. So I am called, how we define the delta function? You define some theta of x minus x prime. If you differentiate it, d by dx, what do you get? So this is the definition of a delta function, is it? You are differentiating a step function, what you are getting? Delta function, is it? So are these equations same? Are these equations same? So in other words, then I can say, so we can say g of x, x prime is simply equal to some theta of x minus x prime. Clear? So much more? Plus some constant of integration, let's call that as alpha of x prime. Because constant of integration will depend on this coordinator. So much more? Because I am doing the indefinite case, so you need to put what? A constant of integration. Clear? So much more? Okay, now if you differentiate it, now just differentiate d by dx of g is equal to differentiation of this thing and differentiation of this thing. So differentiation of this thing with respect to x is 0, and differentiation of this object will give you delta function. So you have figured out what? A Green's function corresponding to the operator d by dx. So it is an indefinite case. Now let's specify the boundary condition. Clear? Okay? Okay. So let's specify. So you are having this x belongs to 0 to infinity. Clear? And y of 0. So y of 0 is equal to 0. Clear? So I need to solve this very equation now. When I specify the boundary condition, I need to solve it. Okay, now tell me what is the solution by the way? Okay, now let's try it. So what is the solution of equation 1? Let's try this as equation 1. What is the solution? So it will be simply y of x, that is simply equal to d of, okay, let's write dx prime, okay, g of x prime, f of x prime. Clear? So what is that equal to? So now tell me what are the limits I am saying? X goes from 0 to infinity. So it is 0 to infinity. So I am having this gx prime. What is g of x prime? So it is theta x minus x prime plus alpha x prime f of x. Okay? Clear? So what is that equal to? So it is 0 to infinity gx prime theta of x minus x prime f of x prime. Okay? Plus then you are having 0 to so 0 to infinity gx prime, then I'm having alpha of x prime f of x. Okay? Clear? Okay, now look at this very integral. So this integral will be what is theta, how theta function is defined? So it is, okay, so you are having theta of x minus x prime. This is equal to 1 for x greater than x prime. It's equal to 0 for x less than x prime. Clear? So it means, okay, so if x is greater than x prime, this is non-zero integral, is it? Now look here, x prime is an integral, okay, dummy variable or the variable over which you are doing the integration, is it? And that variable goes from where? 0 to infinity. But this equation, this theta function demands me x should be larger than what? X prime. So that means it will chop off this integral and put the upper limit to be x. Clear? It will be like this thing. Now you can see 0 to x. Okay, now x should be greater than what? X prime. Okay, if x is less than x prime, it is equal to 0. Clear? So this infinity, you have to replace it by what? X. Okay, so then you can write it as gx prime, simply f of x prime, plus 0 to infinity gx prime, okay, alpha x prime. So this is the solution. Okay. Now let's apply the boundary condition. Clear? So let's say since y of 0 is equal to 0. Samashama? So what is that equal to? So if you put now x equal to 0, y of 0 is equal, you put now x equal to 0, it is 0 here, this is 0, is it? So summation of first term will go 0 plus, now what you will get here? Simply 0 to infinity dx prime alpha of x prime f of x prime. Is that true? So it means, or this 0 to infinity dx prime alpha of x prime f of x prime, that's equal to 0. Samashama? So in other words, this term is equal to 0. Samashama, what is the solution? Therefore, solution is y of x is simply equal to 0 to x gx prime f of x prime. It is the same thing, is it? Now what is the solution of this differential equation? Okay, tell me what is the solution? It is simply y of x is equal to integral of d of x prime f of x prime. Is that true? Is that true? So what are the limits? So you take 0 to simply x. So it was very simple, but we have done it in a complicated way, yeah? Using the Green's function. So it means you are killing a mosquito by a sledgehammer. Huh? Okay. So you got it how to proceed with a solution? Now let's take a more little bit complicated. this very operator, d2 by dxt. Let's try to figure the Green's function corresponding to this very operator. Okay? So what we need to do? So we need to solve this very equation. Okay? Got it? We need to solve this very equation in order to figure out the Green's function corresponding to this very operator. Okay? So it's very simple. Can anybody tell me a trick how we can solve this equation? So, okay, let's say I give you a simple differential equation. Then how you solve it? You integrate out the differential equation, is it? Okay, let's say if you are in first derivative, you integrate once, you will get the variable, is it? You are interested in. If you are having double derivative, simple double derivation, so you just integrate it twice, okay? So isn't it a simple differential equation? So let's integrate it first, okay? So let me integrate it. Okay? So what it will give me? So if I integrate it, it is like this thing. Okay? So d by dx of d by dx of gx prime. Is that true? So let me write. So let's integrate over x. So it will be, what will be on the left hand side? So this d by dx will go. You will be remaining with only this object. So then you will be having integration over, let me write this dx delta x minus x prime plus some constant of integration, okay, alpha x. Okay? So okay, now what is this very integral? That's equal to 1, is it? Is it true? Is it equal to 1? Huh? Or something more? What is the derivative of theta function? So it is, okay, if you write this delta function is derivative of theta function, is it? Oh, emotional. So d by x of theta x minus x prime is equal to delta of x minus x prime. Now if I integrate, integration of delta x is equal to what? You know integration of delta is equal to 1, is it? Okay, but there are actually two domains. That's why I am not putting directly 1. Whether x is greater than x prime or x prime is greater than x. Clear? So since this delta is symmetric in x and x, it is same as x prime minus x. Clear? So that's why I will put a theta function. So it is theta of x minus x prime plus alpha. Now let's integrate it again. Okay, integrate again. So it will give me what? G of x prime, then the integration over this theta of x minus x prime dx, okay, plus integration over this alpha of x prime over x plus some another constant, because it is a double second order derivative. You will have two constants of integration. Let's try that, some eta x. Okay? Clear? So alpha and alpha and eta are constants of integration. Okay? So it is simply equal to integral of theta of x minus x prime dx plus, so you integrate it, it will be simply x alpha of x prime. Okay, because this is alpha of x prime, you are integrating over x. So it is eta of x. Let's call this as equation 1. Okay, so this is the Green's function you have calculated. But what is the problem with this Green's function? You need to calculate what is the integral of this theta function. And I have not defined any boundary condition yet. I want to figure out Green's function in the indefinite case first, where the boundary conditions are not satisfied. Okay, are not given. Okay, we are solving a Green's function equation just for the indefinite case where you don't have the boundary conditions. Okay, then we can impose a boundary condition. Okay, then we can figure out what are these constants of integration. Okay, first I need to figure out without a boundary condition, without the limits, what are the limits here. Okay, we will figure out what this integral is. First we need to figure out the integral of this theta function. Okay, so let's try to figure it out. Okay. Okay, so let's say if you are an integral of some function, you will try to figure out what is the derivative of that function. Okay, while from, let's say this theta comes from the derivative of some another function, you can then write this theta in terms of that derivative and integral will go, it will be there, is it? So let me write it this way. Okay, so let omega of some x prime be a function such that d omega by d of x prime, so that's equal to theta x prime. So let me introduce some unknown function which we are trying to figure out. Okay, so that means this theta function has come from where? Okay, from this omega. We call this omega as the primitive of this theta function. Okay, so you can write instead of this theta as this d by dx of omega, you write it here, integral and derivative will go, so it will be omega there, is it? So but what is unknown to us? Omega. We need to figure out omega. Clear? So how to do it? Yes, so you just integrate it out. Okay, so integrate it. Okay, so what you will get? So I'll write this omega x prime is equal to integral theta of x minus x prime dx, so plus constant of integration. Clear? So when you integrate something, you need to put a constant of integration, is it? Okay. So or I can write like this thing, omega x prime. This is equal to, okay, now if x is greater than x prime, now let me take this case. If x is greater than x prime, okay, so what you will get? So this is theta, so it will be 1, is it? So then you need to integrate integral of dx. What is that equal to? X, clear? Some x plus a constant of integration. Clear? So let me write that constant of integration here, a of x prime. Now if you differentiate it, d omega by, so dx by dx plus differentiation of this will be 0. Okay? Now if x is less than x prime, what will be this objective? This is equal to 0. And then you have again a constant of integration. Okay? Let me call in this case that constant of integration to be b of x. This a and b you can take as same. Okay, but I will take different. Okay, you need to take them different because why you require them to be different? You are actually integrating over different regions. Okay, so here it's a region where x is greater than x prime, and it's a region where x is less than x prime. That's why you require to take them different constants. Clear? Okay. So now let's rewrite it. Okay, so let's rewrite it. So which implies this omega x prime, that's equal to x plus a of x prime. I will write it in this way, theta of x minus x prime. Okay, so this is a solution where x is greater than x prime. Clear? So much plus then you are having b of x prime, theta of x prime minus x. So it's a solution where x prime is greater than x, or x is less than x prime. Clear? Got it? So I have rewritten this in a compactive form. Okay? So now let's differentiate it. Right? Let's try to figure out what this a and b is. Okay? Let's differentiate it. Therefore, d by d of x, so omega of x minus, okay, x prime. So d, okay, differentiate it. Can you tell me? So it will be simply, okay, you differentiate it by product rule. It will be simply a of x prime, theta of x minus x prime plus x plus a of x prime. Then you are having differentiation of this thing, that is delta x minus x prime. Then you are having differentiation of, okay, so the differentiation of this object is 0. So then you need to take differentiation of this thing plus b of x prime. So what is differentiation of this object? We are differentiating with respect to x, okay? So let me write for you theta. So theta of x prime minus x. So this object is actually equal to minus delta of x prime minus x. Clear? That is same as minus delta of x minus x prime. Now look here, differentiation of theta x is the delta of x. Now then you need to integrate, since this x comes with a negative sign. That's why the minus here. You have to differentiate it with respect to x again. Okay? So what it is equal to? Now let me write it. So it is a of x prime theta of x minus x prime plus x plus a of x prime. Okay? So let me write x plus a of x prime minus b of x prime delta x minus x prime. Okay? So this is the equation second. So let's call this as equation third. Now look here. So we started with omega. Okay. And let me again explain. We started with omega such that the differentiation of omega yields me theta function, is it? But once we have calculated this omega, differentiation of omega yields me all these functions, is it? So much out? Clear? So no. It will be, there is no a of x prime. Once you differentiate, it is 0 here. Okay, so there is no a of x prime. Okay, now look here. So you have got what? D omega by d of x, x prime is equal to this object. Clear? So that means when you compare third and second, so you are having this on left hand side, then this object, it is there, then you are having this additional term. This must be equal to 0, is it? So summation, once you compare second and third, it means this object has to be what? 0. Okay? Comparing second and third, use x plus a of x prime minus b of x prime delta of x minus x prime, that's equal to 0. Clear? So this is true for any delta. Delta cannot be 0, is it? So now you substitute, since this is simply this object, f of x into delta of x minus a. What is that equal to? F of a delta x minus a. Okay? So that means this x will be replaced by x prime. So it is x prime plus a of x prime minus b of x prime, that's equal to 0. Clear? So what you have got? So you have got an equation, one equation. You started with two unknowns. Now you arrived at one equation. Clear? So an equation that contains both a and b. A and b were unknowns. Okay. So now tell me how many unknowns are left? Only one unknown. Okay. So if you see, you started with a single order differential. D omega by dx is equal to theta of x. Is it? So it will contain only one integration constant. Okay. So much. Okay. So now let's write this a of x prime. So which implies a of x prime is equal to what is that? So it is b of x prime minus x prime. Yes. Okay. Let's substitute it here. Okay. Let's substitute it in this very equation. Okay. So let's call this as equation something 2a. Substitute it. So what you will get? Omega x prime, that's equal to x. What is a? Plus b of x prime minus x prime theta x minus x prime. Okay. Plus b of x prime theta of x prime minus x. Okay. So what you are having now, you write it as x minus x prime, theta of x minus x prime, okay, then you are having b of x prime, okay, theta of x minus x prime. Just I am rearranging the terms, it is very simple. So this object is equal to identity. So it is, or I can write omega of x prime, that's equal to x minus x prime plus bx. Clear? So this is our omega, is it? What is omega? When I integrate the theta function, it will give me omega, is it? So samajh chalo? So therefore I can write my Green's function. Okay. So let's rewrite the Green's function. Okay. So you have the Green's function like this, xx prime, that's equal to integral dx theta of x minus x prime plus some x alpha of x prime, okay, plus theta of x prime. Clear? So now integral of theta of x gives me omega, because differentiation of omega gives me theta. Clear? So this object is simply equal to what? Is equal to omega of xx prime. What is that equal to? So it's equal to x minus x prime, theta of x minus x prime plus b of x prime. Okay? Then plus x alpha of x prime plus eta of x prime. Since b and eta are constants, so I can mix, okay, I can put a single constant, so like this, x minus x prime, theta of x minus x prime, plus x alpha x prime, plus, let me write that as beta of x prime, while beta is equal to some b plus c. Okay, so you are having now two constants. So this is our Green's function. Because we start with a second order differential equation, it will yield me two constants of integration, and those constants of integration can be figured out from boundary conditions. Clear? What are the, so this is an indefinite Green's function. Here what is unknown? Alpha and beta are unknown for us. Clear? Okay, so now let's impose a boundary condition. Samajh aa? Let's impose a boundary condition. Okay? Let's say okay, so you have this kind of differential equation now. So f of x. So you have this. You have figured out what is the Green's function corresponding to this operator. Clear? Got it? So you have figured it out. Now you are having this very differential equation, and let's say x belongs to some. Okay. So let me check. Yes. Some interval a b such that y of a is equal to 0, y of b is equal to 0. So these are the boundary conditions. They are stated at the ends of this very interval. Okay. So you are having y of a, here it is 0 and here it is 0. So now let's write. Now what is the solution first? Tell me. So let's write the solution of this very differential equation. The solution of equation, let's say it is 4. So I can write now y of x, that's equal to 0. Okay. So sum from a to b, because my limits are where? A to b. Okay. So dx prime g of xx prime f of x prime. Now I have figured out what g is it? So it is a to b dx prime. What is g? So it is x minus x prime, theta of x minus x prime, f of x prime, it is the first term. Then you are having integral a to b gx prime, then you are having x alpha of x prime, f of x prime, then you are having a to b gx prime beta of x. You need, because of the boundary condition, we will be able to figure out what this alpha and beta are. Clear? So this is now our solution. Anybody having any question? Okay, now what will happen? So what will happen to this integral? When, okay, so x is greater than x prime. So you will take upper limit what? X. Okay? So you will take the upper limit x, because b is the value for x prime. So once you integrate out, you are actually B is the A and B are the values for the integration variable. That's x prime. Clear? And this theta demands x has to be what? Greater than x prime. So that means this upper limit should be what? X. Clear? So this theta function. So it is simply a to x, gx prime, x minus x prime, then f of x prime plus a to b. Okay, so you can take this x out because there is no integration on x. So dx prime, alpha of x prime, f of x prime plus a to b, gx prime, beta of x prime, f of x prime. Okay? So now let's apply the boundary conditions. Okay. So let's take y at a, that's equal to 0. So what is that equal to? When you take y equal to a, so that means you take x equal to a. So this integral goes. Is that true? So you put x equal to a, so you are having a and a, so it is equal to 0. So it is 0 plus then, so this x is equal to now a. So it is a integral of a to b dx prime alpha of x prime f of x prime plus a to b dx prime beta x prime f of x prime. That's okay, that's equal to 0. Or I can write this way, a to b dx prime like this. So this a I can take inside. So it's a into alpha of x prime plus beta of x prime, okay, into f of x prime. Just clubbing the two integrals, that's equal to 0. Since f is the source term, it cannot be 0, is it? So we are taking non-zero f. Okay. So it means this integral equation is true for any arbitrary f. Clear? So it implies this object has to be equal to 0. A alpha of x prime plus beta of x prime, that's equal to 0, or let me write, so beta of x prime, that's equal to minus, okay, so let me write a alpha of x prime. Let's call this equation. Now let's take another boundary condition. Clear? Let's take another boundary condition. What that will be? Oh, sorry, you also can look for? Okay. So you can do it yourself, right? Now you got the point. Okay, so let me take another boundary condition. So you take y of b, that's equal to 0. So when you take y of b, so it is b here now. It will be a to b. Okay? So you are having a to b dx prime. So now what I am taking x I am taking b, so it is b minus x prime f of x prime. Okay? Then you are having plus x is equal to b a to b, okay, dx prime. Then you are having alpha of x prime f of x prime plus a to b dx prime beta of x prime, okay, f of x. Clear? Now I have already figured out beta. Is it true? I have already figured out beta. Yes. Have we done anything wrong? Yes. No. So now let's take. So or I can write it as a to b dx prime. So let me take. Let me club up the terms. So it is b minus x prime plus b alpha of x prime plus beta of x prime. Okay, whole multiplied by this f of x prime, and this is equal to 0. Okay, so you can now use beta is equal to minus a here. Okay, so using this up. Okay, or I can write. So let me write, which implies b minus x prime plus b alpha of x prime plus beta of x prime, that's equal to 0. So what is beta? So or I can write b minus x prime, okay, plus b alpha of x prime minus beta is actually minus a alpha of x prime is equal to 0. So which implies, so I am using here. Okay. So now let's what I need to figure out. What is unknown? Unknown is alpha. So it's b minus x prime, okay, plus b minus a into alpha x prime, that's equal to 0. So what it gets? Gives me alpha of x prime is equal to b b minus x prime with a negative sign here. So now we have figured out both alpha as well as beta. Okay? So therefore, what is beta now? Therefore, beta of x prime is equal to minus a times, so it will be simply a b minus x prime. B minus. So now let's write the Green's function now, complete Green's function. Okay? So you have figured out both alpha and beta. Now if f is known to you, you can solve your equation, is it? So now let me write what is the Green's function. Therefore, this g of x prime, that's equal to anybody? X minus x prime, theta of x minus x prime. Then what was there? So it is what was that? Yes, it was something x times alpha of x prime. So it will be simply minus alpha prime is like this, minus b minus x prime divided by b minus a, okay, multiplied by x. Then you are having plus beta of x, so that's a b of x prime divided by b minus. Clear? So this is your Green's function. Now unknowns are gone. Okay? So this is the Green's function corresponding to this very equation. Okay? Okay, so you can rewrite it. Okay, you can put x minus a, yeah? So, or I can write g of x prime is equal to x minus x prime theta x minus x prime plus a minus x, okay, a minus x into b minus x prime divided by b minus. So what we are having here, x and x prime both reside where? Okay? Any question? So what is time now? Okay, just stop here. Just wait here. So I will get the question.